I'm Yongle Zhang from University of Toronto. And today I'm going to introduce Iprof, which is a non-intrusive request flow profiler for distributed systems. This is a joint work with my colleagues from University of Toronto. Today, large companies rely heavily on data centers, which are built as distributed systems. So poor performance of distributed systems can lead to increase of user latency and increase of data center cost. So diagnose distributed system performance and improve the performance can reduce its cost. However, distributed systems behavior are complicated and hard to understand because they serve concurrent requests spread across different nodes. So to diagnose these performance problems, developers need tools to help reconstruct the request control flow and understand the system behavior. There are a lot of tools that have been built to infer this request control flow. However, they are intrusive because they modify some part of the system, and they incur performance overhead, and the instrumentations are often system-specific. Our work is based on the observation that system logs already contain rich information to diagnosis. This is not a coincidence, because developers rely on logs to perform manual debugging for these complicated systems. And as an evidence, nowadays distributed systems already generate large amount of logs during normal execution. For example, NetApp and Facebook already generate terabytes of logs. So because of this, a lot of tools have also been built to try to utilize this information in logs, but they are limited in that they cannot infer request control flow. For example, machine learning-based log analyzers, they can detect system anomalies by recognizing abnormal log patterns. And also some commercial tools like Splunk and VMware Log Insight, they index the logs and require users to perform keyword-based searches. In comparison, Iprof is a non-intrusive profiler. It can infer request control flow from system logs along with timing information. It can group logs printed by the same request on multiple nodes using information generated by static analysis. And the key idea of Iprof is to use information generated by static analysis to group logs. In the rest of my talk, I'm going to use a case study to show how Iprof can be used to diagnose a real-world performance problem. And next, I'll describe the design of Iprof and the evaluation of Iprof. This real-world example is a performance regression of HDFS, which is a Hadoop distributed file system. And the user suspects there is some performance degradation after HDFS update, but without any tools, he don't know what the problem is. And with Iprof, user can get the latency for different types of requests in the system. And this is a screenshot from Iprof's web user interface. The y-axis is the latency, and the x-axis is the real-world time. Each line in the graph represents one type of request, with each point in the line as one instance of the request. So the red line in the graph is a write block request in HDFS. And the black line is a read block request in HDFS. So from this graph, it is really clear that after the HDFS update, the latency for write block jumps, but not for read block. So user might further want to compare normal write block request with abnormal write block request after the HDFS update. Iprof can provide how these two requests are processed on different nodes. And so this is another screenshot from Iprof's web interface. On the left side is the normal write block request. On the right side is the post update write block request. So for HDFS write block request, it will traverse 3 nodes, and the latency on each node is inclusive, which means data node 2's latency will include data node 3's latency and the network communication time. So from this graph, it's clear that the latency on data node 3 doesn't increase, but the latency on data node 2 and data node 1 increases, which means the local processing time on one node doesn't increase, but the internode latency increases. This suggests that there might be some additional network latency introduced in the communication between the nodes. And actually, the root cause is there are additional and necessary network communication, which is introduced in the new HDFS version. Next, I'm going to explain how Iprof is designed to perform this kind of diagnosis. Iprof is mainly composed of static analysis and log analysis. Static analysis will take bytecode as input and generates the necessary information, which we call model. And log analysis will use this model to analyze the real-world system logs and generate a request database. Each record in the request database describes one request control flow, and it can be further used for visualization. So the main challenges involved in Iprof to achieve its goal, which is group log messages printed by the same request. Well, I'll show these challenges using a HDFS log example. So first, the first challenge is that logs are interleaved. This appears in 2 forms. First, logs printed by different request types are interleaved. Like in the example, the logs printed by read block appears in between the logs printed by write block 1. The second form is that logs printed by different requests of the same type are interleaved. We see logs printed by write block 2 appears in between the logs printed by write block 1. The second challenge is that we need to differentiate every single request, but a perfectly unique identifier doesn't always exist. As in the example, although block ID can differentiate the 2 write block requests, but it cannot differentiate write block request 1 with a read block request because they are operating on the same block. And finally, the last challenge is that logs printed by one request often spread across multiple nodes. Like the logs printed by write block request appears on both data node 1 and data node 2. We'll use the example code in HDFS which prints the previous logs to explain what type of information Iprof needs to solve those challenges. So first, to differentiate those request types, we need top-level method, which we define as the starting method to process a request in a thread. Like the write block method, it is a starting method to process write block request in a thread. And second, to differentiate requests of the same type, we need request identifier, which we define as a frequently logged variable, which is not modified in one request. And the third information we need is a log temporal order, because we further want to differentiate requests that are of the same type but print same request identifier. We define it as a possible order between log statements in one thread, and such as the consecutive order between the two log messages in packet responder. And the last information we need is how threads communicate with each other in order to group logs printed by different threads for the same request. Like in the example, write block communicates with a packet responder through thread creation. Next, I'll describe how lprof infers these four types of information. So first, lprof use one pass of analysis, which we call request analysis, to infer both the top-level method, which is starting method, and the request identifiers. The intuition behind this analysis is that the developers already log important information in order to differentiate the requests and do manual debugging by themselves. So they need to make sure that these identifiers stay the same within one request, so that we know that once these identifiers are modified, we are outside of a request. And this is how we pick the top-level method, which is a starting method. Request analysis is performed as a bottom-up data flow analysis on the call graph. So first, lprof will treat every logged variable as an identifier candidate, and also the number of times they got printed will be kept as a count. So these two information will be propagated in a bottom-up manner through the call graph. And once the identifier candidate is printed, lprof will increase the count. Once it's modified, lprof will remove it from the set. This is a call graph for this HDFS example. So from the bottom, we'll see that in write block and read block method, block ID is never modified. So, and also it's printed 8 times and 7 times respectively. So they are identifier candidates. However, when we go to the upper level method, which is data exhibitor, we'll see that block ID got modified. So it's removed from the identifier set, and the count decreases to 0. This indicates that the frequently logged variable is modified, and likely we are getting out of the request. So we pick the top level method as a write block and read block instead of data exhibitor. Also, we pick block ID as a request identifier. Remember, the next type of information we need is a log temporal order. And lprof performs a control flow analysis on a call graph in each top-level method to infer this temporal order. In the example, receive block and terminating these two log messages are printed consecutively in packet responder, and lprof can infer this consecutive order between them. So if in a real log, we see that a terminating log message is printed before the receiving block log message, we will know that this is not a possible log message sequence printed by one request, and we can attribute them to 2 different requests, even if they have the same request identifier. The last type of information we need is a communication pair between different top-level methods. First, within each node, they can communicate through thread creation or shared objects. And between nodes, they can communicate through sockets or RPC. Especially for network communication, we pair serializing and deserializing methods from the same protocol instead of pairing the sending and receiving method from the same socket. It's because a lot of top-level methods, they communicate with each other. They are sharing the same socket, but they are not really communicating with each other. And to summarize the static analysis output, first, we need the top-level method to differentiate requests And second, we need request identifier to further different requests with the same type. And we need log temporal order to differentiate requests with the same block ID or request identifier. And then we need communication pair to group logs printed by different threads. And we use this model to further perform the log analysis on real-world logs. So it is implemented as a map-reduce job. First, in the map phase, Iprof will use the temporal order request identifier top-level methods to group logs printed within one top-level method. And in the combine phase, Iprof will use a local communication pair to group top-level methods that are locally communicate with each other. These two phases are performed on the same node where the log is located. And last, in the reduce phase, Iprof will use global communication pair to group logs printed by top-level methods on different nodes. In the evaluation of Iprof is evaluated on logs from 4 different distributed systems, including HDFS, YARN, HBase, and Cassandra. And logs are generated on 200 nodes using high-bench and YCSB workload. And to verify whether we group logs correctly, we manually verify each unique log sequence, which means, as in this example, this is a log sequence for write block request. It consists of 9 logs. And for all the write blocks that print this log sequence, we aggregate them together and verify once for all of them. The result for this accuracy evaluation is that over 90% of the logs are correctly grouped with different requests. This indicates that Iprof is indeed leveraging the developer's logging effort to different requests for manual debugging. And on average, 5.7% of the logs are incomplete, which we define as logs we are unable to group. And the main reason for this part is there are some identifiers in YARN, which is parsed through complicated data flow. And right now, the current data flow analysis in Iprof is not aggressive enough to trace it. And there are also 3% of the logs we cannot parse, so we categorize as a field, and 1% logs we added to the incorrect group. Next, we evaluated Iprof on real-world performance anomalies. We randomly select 23 real-world anomalies and reproduced each one to collect logs and use Iprof to analyze the logs. For 65% of them, Iprof can show the anomaly and help user guide him to the root cause of the anomaly. And in the remaining 35%, most of them is because abnormal requests don't print any log messages, so Iprof cannot help. And also some other cases, the abnormal requests only print 1 log message, but the latency is needed for debugging that. And Iprof at least need 2 log messages to infer the latency. As for related work, we have already explained that existing tools are either intrusive or cannot request control flow. And in comparison with the mystery machine, which is presented on Monday, they can infer request control flow across software layers, while we can't. And they can analyze critical paths and slacks, but they still require instrumentation on existing logs. To sum up, we designed and implemented Iprof, which is a profiler for distributed systems. It infers request control flow from system logs along with timing information. It is non-intrusive because it's entirely based on analyzing system logs with information generated by static analysis. And Iprof does all this through the observation that developers already log important information in order to different requests and do manual debugging. Next, I'm going to do a quick demo to show lprof in action. We use a 5-node HDFS cluster, and we collect the logs this morning, analyze it, and this is a type of information lprof can provide. So this is the same type of information as in the case study, latency of each type of request. We can zoom in to a specific time area, and we can actually click on one of the requests to see the latency. And we can also check all the request count by different request type. These are the requests, some type of requests in HDFS. And we can also check the request count for different type of requests on each node. And we can also perform this latency, see the latency, average latency on each node for each type of request. And this information is based on the query you perform on our database. So you can write different queries to get different informations. And I'm happy to take questions.
Hi, Rodrigo Fonseca from Brown. So I have a question. So if you had, could tell the developers of these systems how to augment their logs, perhaps like to make sure that you would be able to capture everything that you need, what would you tell them?
Sorry, I didn't get that.
If you could tell the developers to add little bits of, to improve their logging such that your tool would have a better performance, what would you tell the developers?
Oh, thank you. So lprof analysis will tell you that within one request, there are some logs that have identifiers, some logs doesn't have identifiers, which will be captured by our log temporal order. And it will suggest that you should add request identifiers in these log messages. And this is kind of one type of suggestion that lprof can make to the developers.
Yeah, I like that idea. So the other question, how would you extend this to for example, to make sure that you can combine the information from HBase and HDFS, for example, because you currently don't do that, right?
Yeah. So right now we don't infer this request flow across software layers, but actually that's our next project. We are kind of working on that.
Thank you.
So Hao Mai from Hortonworks, and I develop HDFS. So I have a in production system that we actually logs a lot of metrics. It's like the latencies and what kind of anomalies we have, and we have to put everything into HBase or even Azure or something like that. So can you comment on how I can actually combine these the metric system and the log analysis to actually help me to find out the anomalies in the production settings?
Sorry, can you describe the metric system again?
So in production, we log, for each node, we log how many bytes we process each minute, and what kind of, how many blocks that we takes way too long to handle, and something like that.
Oh, yeah, thank you. I think lprof is so what you log is for each node, the latency and different type of information. But what lprof does is it stage all the log messages for one specific request, and it tells you how this request is traverses all the node. So it aggregates the information on different nodes and provides you this information for a specific request. So I think this is they can help each other in that. That metric is analyzing per node information, and lprof is help you to understand that the information for each request which traverses in the system.
One more question.
Hi, Eris Pepe from NC State University. I have a question about this. I saw the example is like receiving and sending blocks. So how about the block replication and the block deletion in HDFS?
Block replication?
Yep.
You mean like recover?
Actually, in HDFS, the log is not only like like a block, like sending or receiving. Like HDFS has its own mechanisms to management of those blocks.
Yeah.
So have you considered this block replication deletion, this management into the profiler?
Okay. So we show that those log messages, because it's representative, and often it's a start log message and end log message of the one specific top-level method or a request. And lprof is really efficient in recognize this message that marks a start and the end log message. So as far as lprof can recognize the start and end log messages, lprof can reconstruct that how this request is processed in this thread. And the other logs, I assume you are talking about the other logs that printed between these log messages. lprof can still use a block ID and log temporal order to group them in this thread. But the most important part is start log message and the end log message.
But actually in the performance issues, like replication, like block management.